So today we're going to continue looking at clustering algorithms, and we're going to start with hierarchical clustering. And the idea of hierarchical clustering is to create groups together, so group examples in smaller groups and then larger groups and so on. This is an example of hierarchical clustering. We have the tree of life, where we have groups of organisms like animals, fungi, and things like that, and then we can group them into higher hierarchies, and even these groups are groups of organisms. So the basic idea that we're going to look at today in this first lecture will be hierarchical clustering, two different approaches to hierarchical clustering: agglomerative clustering, where we start from the bottom and group examples together and then group groups into larger groups, and divisive clustering, where we start with everything as a single group and then split and split again until we have the final level of if we do the whole three individual examples, or we can stop somewhere in between. And then we're going to look at an example of using clustering, but instead of clustering examples, we're going to cluster features and then simplify our attribute space, so the space of features we're going to use. So this is the basic idea of hierarchical clustering, grouping together groups. We can use them in many different examples. This would be to group together different organisms. In this case, we have different patterns of gene activity, but we are interested not only in grouping those that are very similar together, but in following up those similarities further on in this hierarchy. So we want to see genes that have an activation pattern that is very similar, but then groups of genes that are also somewhat similar, not as similar as within each group, but more similar between the groups than to any other group, and so on. So we can draw this kind of tree with representing the similarity between the examples and the groups of examples. So this is the basic idea. We can represent hierarchical clustering as a dendrogram, as a diagram of this tree-like diagram, where we represent on the three branches the different groups that we are making. For example, suppose that we have these examples, and we find that B and C and D and E are very close together. So we can represent this as joining together B and C into the BC group, and then D and E into the DE group. And then we have this F here, which is close to the DE group, so the F comes in later. And now the two closest things are these two groups, the BC and the DEF group. So we join them together into this larger group, and then finally A comes in because A is very far away from the rest. So we can represent a hierarchical clustering of these data using this dendrogram, this tree-like representation of which elements come together first and then which groups are bunched together into larger groups. So first, to do this, we need, of course, some measure of how alike individual examples are. We saw this in clustering in general. There are several terms for this. For example, proximity is sometimes used as a vague term for likeness, for being alike one another. Similarity is generally used more specifically to indicate a measure between 0 and 1, for example, of how alike the examples are. Dissimilarity would be the opposite of similarity, so instead of measuring how alike they are, we are measuring how different they are. And distance is a special case of a similarity measure which respects these conditions. It must be greater than 0, so all distance between points must be at least 0. If it's 0, they are coincident. If they are not coincident, then it's greater than 0. The distance is symmetrical, so if you measure distance from x to y, it must be the same as y to x, and it must respect this triangle inequality. So the distance between x and some point z cannot be larger than the distance between x and y plus the distance between y and z. So the distance between 2 points cannot be larger than some other path from one point to the other. So if you have a measure of dissimilarity that conforms to these constraints, then it's a distance measure. Some measures of distance often used are those in the Minkowski distance space. We have Euclidean distance, we have squared Euclidean distance, Manhattan, and so on. So all of these respect those constraints and are distances. There are other variations, other types of distance that are sometimes used. For instance, the Mahalanobis distance is a distance normalized by the variance or the covariance matrix if you use many variables. So basically, we have distance, which is this cross product of the two, the dot product of the two vectors, the transpose and the vector. But then you multiply by the inverse of the covariance matrix. This means that in any direction where dispersion of your data is larger, distance counts less. And in those directions where your data is less dispersed, distance counts for more. So basically you are scaling your distance measure according to the dispersion of your data, the shape of your data. Then you have other situations. For example, you may want to compare strings. This Hamming distance is simply the count of the number of characters that are different in different strings. This Levenstein distance is an estimate of how many additions, changes to the string you must make to go from one to the other, where changes can be replacing characters, inserting characters, deleting characters, and things like that. So you may have, for different kinds of data, different measures for similarity or distance, and so on. But this is a general problem for clustering. We need to measure somehow how alike or dislike different the points are, the examples. But with hierarchical clustering, we also need to measure the differences or similarities between groups. And this is called linkage. So linkage is basically the measure we use to determine if two groups are close together or not. And this is something that you don't need in partitional clustering because you're not grouping groups together, you're just grouping examples into groups. But in hierarchical clustering, you need to do the same to groups, so you need to have these linkage measures. These are a few examples. Single linkage is, we measure the distance between two groups as being the smallest distance between the groups, so it's the minimum of the distance between any point in group J and any point in group K. Complete linkage is the maximum, so we are taking the points that are further apart between those two groups and use that as a distance between the two groups. We can do the centroid linkage. We compute the central point of each of the groups and measure the distance. And there are other examples. We can take all the distances and compute the average, the mean, or the median, or we can try to minimize the sum of square errors. So this function is for all the points that belong to a cluster, we add the squared distance between the points and the cluster. And then we do that for all the clusters. And we may want to group clusters together in order to minimize this value. So group things together that make the sum of the squared distances inside each cluster as small as possible. So basically, to do hierarchical clustering, we need to have some way of measuring the differences or similarities between examples, and we need to have some way of comparing clusters of those examples. So in the first part, it's the same as partitional clustering, because we can only cluster if we can measure some similarity or difference between the examples. But we need also that linkage. We need to be able to do the same with groups of examples and not isolated examples. Some advantages of hierarchical clustering. One considerable advantage is that we do not need to assume anything about the number of clusters, and we can actually control or choose the number of clusters after we do the clustering. Because once you have the complete hierarchy, you can decide at which level you're going to do the clustering. And also, this hierarchical organization may reflect something about the data. It may be meaningful, and so the hierarchical clustering is especially useful in those cases if this hierarchy is actually telling us something about the data. For example, when you're grouping living organisms together, or genes, or something like that, where this tree represents something about the data. The disadvantages are that hierarchical clustering is trying to solve a combinatorial problem with a very huge space, because you need to to go through all the possible groups of all the examples. So generally, we do not do that exhaustively. So basically, you're doing a greedy approach with a single pass, and any mistake that you make along the way will not get fixed further on. So this is one problem with hierarchical clustering. You are only exploring a very small fraction of the possible space for all these groups. And also, if the hierarchical organization of the data does not reflect anything interesting about the data, this may actually be more confusing than just doing partitional clustering. So whether or not you should use hierarchical clustering depends on whether you want to use those advantages and do not have to deal with the disadvantages. So two basic approaches to hierarchical clustering. We can start at the bottom with all the examples in individual clusters and then start grouping them together until we group everything into a single cluster. In that case, bottom-up approach is called agglomerative clustering because we are joining them together. So basically this starts with singleton clusters, so clusters of only one example, and then we use the linkage metric to try to find out which groups of one example we should bring together and then which groups we should add to those and so forth. This generally takes the order of complexity, time complexity for this algorithm is on the order of the number of points raised to the cube. So it may not be very good if you have a large number of points, although you can speed it up with linkage constraints, by which you specify which pair of points can be used to join groups together. We're going to see an example of that. The top-down approach is called divisive clustering because you start with a large cluster with everything and then you split it. Split it into a number of subclusters and then you pick one of those clusters, split it again, and you keep doing that until everything is either in a singleton cluster, so you only have clusters of one example, or you just reach the level that you wanted and just give up. In general, if you want to do an exhaustive search with divisive clustering, the time complexity would be 2 raised to the number of points, because that's all the combinations that you can have. However, in practice, it's not as bad as that, because we can use a fast algorithm for doing these splits, and so we generally do not explore all these combinations. Also, it can be better than agglomerative clustering if you only want a few clusters from the top, because if you do it bottom up, then you have to do all the computations until you reach a small number of clusters. If you do it bottom up, if you do it from the top, you can do just a few steps if you don't want many clusters. So this will depend on the kind of application that you want. So let's see an example of agglomerative clustering just to visualize this. We start with examples split apart into individual groups, so each group is a singleton, has only one single example. And now we iterate by looking at those which are closer together, grouping them, and then find another case where they are closer together, grouping them, and so on. So basically you can see that the searching for the pair that is closer together is on the order of the number of points squared, and then doing this for each point you get on the order of the number of points cubed for the time complexity for this algorithm. So this would be how the agglomerative clustering works, and as you can see, if we record all of these agglomerations when we bring two groups together, we can start to draw the tree that represents this hierarchical clustering. So we can translate that into a tree where we represent each grouping, and then each time we add a new element to a pre-existing group, or join two groups together, and so forth. So we can represent what we are doing here along the algorithm. And this would be the result of the agglomerative clustering. We don't have a specific partition of our elements into different clusters. We have the representation of all the nested clusters we put our examples in. So if we want to convert this into a partitional clustering, that is, we want to take this tree and divide our elements into a partition of clusters, then we can simply choose one level on the dendrogram which has the clusters that we want. For example, suppose that we break this down into these two branches of the tree. We have two clusters here. So we can divide all our data into these two clusters by cutting away the last branch of the tree. We can do the same thing with three clusters, so we cut away also this other branch, the one before last branch, and we have these three clusters, and we can do this with as many as we want. So if we cut away the last three branches, we have 4 clusters, 5 clusters, and so forth. So it's easy to go from the hierarchical clustering into the clusters that we want, the number of clusters in a partitional clustering. We just cut the tree at the level that we want. So basically we can decide how many clusters we want to have in the end, if we want to do partitional clustering, from the same hierarchical cluster which reflects all the structure on the data. So we don't have to compute anything again by changing these parameters. Also, agglomerative clustering is not very good for large data sets because of that time complexity, and sometimes we also may want to restrict the linkage, the groups that may be brought together, in order to better reflect some structure in the data. For example, we may not want to cluster everything like this, where these points, for example, belong to the same cluster. So since they are close together in distance, they will tend to be in the same cluster. But we may wish to impose some constraints on which groups may be brought together in order to restrict the way the clusters are made and avoid this problem. It also helps if we constrain which groups are brought together. It helps reduce the time complexity because that search for which groups to agglomerate will be faster. So we can do this by providing this structure via connectivity constraints. So connectivity constraints can be represented as a matrix which has n by n, where n is the number of points, and where you have a 0 in all those pairs that cannot serve as a link between two groups, and a 1 in all those pairs that can be used to link groups together. So we can use scikit-learn to create this matrix. For instance, creating a matrix with the nearest k neighbor on our data. For example, we can use the k neighbors graph, to which we give our data set. Must be one element per row, and one example per row, and one feature, one value of the position per column. And then we tell how many neighbors we want, and basically this returns a matrix of n by n, where it will have a 1 every time these 2 points are within the 10 neighbors, 10 nearest neighbors of each other, and a 0 if they are outside the 10 nearest neighbors. So you can imagine this connectivity constraint by assigning to each point and only allowing linkage to points that are within the 10 nearest neighbors. And we do that for all these points. So basically we are creating this connectivity constraint matrix here, and now we do the agglomerative clustering with that connectivity constraint. And this is the difference. This is without constraining connectivity, so points are brought together merely by their distance, or if we restrict the linkage of the group to only those points that are within the 10 nearest neighbors of one another. So in that case, linkage will go through this ribbon, because usually the points within the 10 nearest neighbors are within the same part of the ribbon and do not reach to the other side. And so linkage can only occur along the ribbon here. And we have this cluster, and so forth. We don't have these kinds of clusters like we did when we did not impose connectivity constraints. So basically we can do agglomerative clustering and fine-tune it to the shape of our data if we impose these kinds of constraints. So these are some examples of the parameters you can use in agglomerative clustering. You can use the kind of affinity you want, if it's Euclidean or there are some others. The linkage too can be complete, average, or word. Word linkage assumes Euclidean distance. You cannot compute that without Euclidean distance. And in general, words, if you can use Euclidean distance, word connectivity tends to perform better, because complete linkage tends to favor larger clusters. They tend to become larger if they are already large. because you are looking at the longest distance between the clusters. And average linkage solves that partially, but does not really work as well, at least when we have Euclidean distance, doesn't work as well as word linkage. However, if you don't have Euclidean distance, you cannot use word linkage, so you can try average linkage or complete linkage. So now let's see the other type of approach, which is to start from the top and divide things. An example of that is the bisecting k-means algorithm. We start with a single cluster, all the examples in a single large group, and then we use k-means with a k equals to 2 to split that into two clusters. And then the iterations consist in selecting one of the clusters, possibly the one with the largest number of elements or the one with the largest spread or something like that, but we have some criteria to select the next cluster, and then we apply k-means with k equals 2 to that cluster and bisect it again. And we do that until either we reach the number of desired clusters or we have each example in a singleton cluster. So each example is its own cluster. So this would be the example. We start with the large cluster and we split into two, and then we split each one into two, and we keep doing that until we have examples which are isolated, and we can pick the clusters by, for instance, the sum of squares distance or the number of examples or something like that. So the idea is that we go in a sequence, splitting the larger groups into smaller groups. Note that we are not exploring all the possible combinations, so we are avoiding that complexity problem of the whole search space being 2 raised to the number of points by just cutting across these bisections using some criteria for selecting the clusters. So this can be quite fast. If we use a fast algorithm like k-means, this can be a lot more efficient than in theory it would be if we explored all the possible combinations. Once again, we can store or remember these divisions. In this case, we are building the tree from the top down. In the agglomerative clustering, we were building the tree from the bottom up. So one advantage in divisive clustering is that we can stop at any time and still have a tree. If we start from the bottom with agglomerative clustering, if we stop in the middle, we have disjoint branches of the tree because we don't know where they join at the end. With divisive clustering, we always have a tree. The only difference is that we may have leaves with more than one example if we don't follow everything to the end. But we can again do partitional clustering from this hierarchical clustering by deciding where we cut on the tree. Although in theory the exhaustive search would have a complexity of 2 raised to the number of points, we can, and also we need to use an additional clustering algorithm. So this divisive clustering is not the whole algorithm. You need some algorithm to do the division step by step. In practice, it can be good because you can use a fast algorithm to do the split. You can use some heuristics to cut across that large search space. And also, you can stop at any time and you have a tree. So if you want a tree and you don't need to go to the end to have all your examples into singleton clusters, then you can just do as many iterations as you want and you still have the tree at that level. So now let's see a different example of application for clustering, which we'll use agglomerative clustering for this one. But the idea is that instead of clustering examples, we are clustering the features. So we are going to try to simplify the features of our data set using clustering. So let's say we have a table of data, just like you're used to use, where each row is an example and each column is a feature. If we use clustering on this data, we are clustering different examples. We are putting different points together according to how similar they are. But we can imagine that we transpose this table. So now we have features on each row and the examples on along the row, so on different columns. So what this would mean would be for feature 1, this would be the value in example 1, the value of that feature in example 2, and so on. So basically we transpose the matrix And now we could do clustering again. So if we were doing supervised learning, if we have examples with some class, if we transpose the matrix, then we don't have anything of the same kind, because there is it makes no sense in assigning class to a feature instead of an example. However, with unsupervised learning, we are just looking at the structure on the data, so these two tend to be symmetrical. It's basically the same thing if you have vectors of features, each one corresponding to an example, or if you have vectors of examples, each one corresponding to a feature, because they're all vectors of numbers, and there is nothing there that's different. There is no column there that corresponds to a class or something like that that is different from the other. So we can use clustering to group together the features that are most similar, and then combine them, aggregate them into a single feature. In this way, we can simplify the features we are using by grouping together those features that are less informative apart, because they are most similar to one another. Let's see an example of this using this written digits data set. You have this data set in scikit-learn. This is a data set with about 1,300 or something like that handwritten digits. Each one was digitized into an 8 pixels by 8 pixels matrix with grayscale. So you have examples of zeros, 1, 2, 3, and so forth. So each of our data, so this is the number of examples that we have, 1,797 digits, and each one has 64 features. If we transpose this matrix, we can consider that we have 64 examples, each one with 1,797 features, corresponding in the first case to, for example, the pixel there on the corner, all the values of that pixel in all the handwritten digits we have in our database. And the second one will be, for the second pixel, all the values in our handwritten database, and so forth. So basically, we can do that. We can transpose this matrix into 64 rows and 1,797 columns corresponding to the rows corresponding to the pixels, and the columns corresponding to the different images we have of the handwritten digits. Now we're going to cluster these 64 into 16 clusters using agglomerative clustering, but we want to restrict the clustering to group together only pixels that are adjacent in the image. So even if one pixel here has values that are similar to another that is somewhere else in the image, we don't want them to link together unless there is a region of similar pixels that makes all of these be a single cluster. So we're going to include this linkage constraint, this connectivity constraint, by forcing the agglomerative clustering algorithm to go only along those pixels that are adjacent in the image. So this is our original data. With scikit-learn, we can use this grid-to-graph function where we say the dimension of the grid. In this case, it has the number of rows and the number of columns of each image. So basically, it's 8 by 8. And we get a connectivity graph of all the neighbors inside that matrix. So basically, we have a 64 by 64 matrix, which tells us for each coordinate if another coordinate is adjacent or not to that one. So this is a simple way of building that connectivity constraint, where we only want to agglomerate groups if they correspond to adjacent pixels. Now this is basically loading the digits from the data set, getting the images, reshaping the images into a single matrix. So we want to have each image corresponding so each pixel corresponding to a large row in this matrix, where we have the values of that pixel for all the images. Now we create the agglomerative clustering object. We are going to use this feature agglomeration, so in fact we do not need to transpose the data ourselves. This is what the feature agglomeration does. But basically, this is the same as the agglomerative clustering algorithm, only it does the transpose automatically and the transform of the data. And now we fit it with our data, and we obtain the reduced representation with the clustered features, and also we can project it back into the same shape of our data to see the result. So basically, we have this original data. This is the representation of the cluster. So these pixels here were considered to be very similar. So basically, these are the block of pictures that are here to the right of each digit, which tend to be very dark. So in clustering, they were grouped together. There is one pixel there that seems to vary differently from those around it. Then these here are similar, these are similar, and so on. So this is a representation of the regions in the image that tend to be more alike in the different digits. And now we can take the original data, and we do this part here where we transform to obtain the reduced data, where we average those values of the pixels within the same region, and we can do the inverse transform where we project it back to the original image. So basically, we reach the conclusion that all these pixels belong to the same region. We average them, and we project back to this transformed data. So you see, this is the original data, and this is the data with the pixels averaged across each cluster. So all of those here on this block are averaged. All those on this part here, for example, are averaged too. So you see these blocks here where they're averaged, and so forth. So now we basically have reduced from 64 features to 16 features. We can represent it like this by projecting back into the original shape, or we can represent each digit now with only a 4x4 pixels image which has the 16 features that we have. So this would be the representation of the different clusters. Note that in this case we no longer can recognize the digits because it's not, each pixel here is representing one of these regions, so it no longer has the shape of the pixels. But you can see that they still have difference. So this is all the zeros, and they are more alike to each other than all the ones, and so forth. So we are sort of changed the alphabet. We lost a lot of features, but we did not lose that much of the information. And maybe we could still do something with this more reduced data set that might even improve, for example, if we wanted to do classification or something like that, because if our clustering reduced the noise in those features and retained the information that we want, this could even improve the performance of the classification. So this is an example of using clustering instead of using it on examples, using it on the features to reduce the dimensionality of our data. So to sum up this part, we saw hierarchical clustering, this idea that we are not only clustering on the same level of the partitions, but we are nesting clusters inside each other. So in order to do that, we need to be able to measure differences not only between examples, but also between groups of examples. And we saw those different linkage measures that allow us to do that. Then we saw two approaches to hierarchical clustering. Bottom-up, where we start with the examples isolated and we group them together in sequence until we have everything into one cluster. If we do that, we get the hierarchical tree, but only if we do it all the way to the end. Until we reach the end, we have disconnected branches of the tree. The other possibility is to start from the top and divide everything and keep going down. So this divisive clustering, if we wanted to explore all the possibilities, it would have a huge space of possibilities, 2 raised to the number of points. But usually we use some kind of quick algorithm for clustering, for example, k-means with k equals to 2, and we do the bisections like that. So we use this kind of heuristic, greedy approach to explore this space more quickly. We also saw a bit the effects of different linkage options and how we can use clustering to group together features instead of examples. The big difference between supervised and unsupervised learning is that in supervised learning you have some additional data in your training set that will be missing in the real application example, and you want to fill it in. So in supervised learning there is something special about that class column or the value that you want to predict or something like that. In unsupervised learning you are just trying to transform the data into something that is more useful or more meaningful. So all the data is just data. You can consider it symmetrically whether you are looking at the features or the examples, and so you can also use clustering to cluster features and thus simplify your your dimensions, the dimensions of your space. There are some documentation on clustering if you want to look for in demos in scikit-learn, both for hierarchical clustering and for partitional clustering, and in Alpython you also have something about these algorithms.